Let's get started. So, thank you so much for everybody who showed up to the workshop today. As you guys can see, we're going to be talking about unsupervised machine learning, which, in my opinion, is one of the coolest types of machine learning because it's less intuitive at first, but I feel like you're able to gather a lot more insights from the data through it. But yeah, I'm excited to go through the workshop with you guys today about it. So if you guys don't know already, this is the Road to AI Data, day number 3. We have 2 more days of workshops. Tomorrow is going to be vision models, and the last day, tomorrow is going to be hosted by Sarush, and then the last day I'll be hosting is how to win AI data. I would definitely show up to that have, uh, if you guys are going to be there for the Datathon. It's going to be really important that you kind of understand what's going on, or else you might be a little lost the day of. But anyways, this is day number 3. We're gonna be going over unsupervised machine learning, and I'm gonna be doing a code walkthrough similar to what I did the first day with intro to or exploring your data or intro to EDAs. So yeah, without further ado, I could yeah, I think we could just jump straight into it. So. Again, like I said before, I should probably say this now. This is going to be like a code walkthrough. So I would say, especially for the people who might have missed that at the start because I wasn't recording, I would definitely recommend having like a notebook open up beside this and just like code along with me. And I think doing that is like good to start building muscle memory, and it's better than just looking at the screen. Um, but today, I'm going to be going over things a little bit quicker as well. I don't want to go too slow because there is a lot to go over today. So if you miss anything, feel free to ask in the chat, or if you're confused about anything. And at the very least, the recording's going to get posted tonight, so you could go back and watch that if you feel like maybe I explained it, but maybe you didn't understand the first time. So. Unsupervised machine learning. First of all, before we really get into it, or I could probably explain this in a little bit. I'll explain it right now. So, unsupervised learning is one of the two main types of machine learning. There's supervised and unsupervised. And basically, and am I able to draw? Yeah. Okay. So the whole idea of supervised versus unsupervised machine learning is that in supervised learning, the model is given a set of input features, and we could label it as X, and then output features. And this is going to be turned into a model that basically maps X to a set of labels, Y, right? So you give them a set of input and output features, and it's going to create this model that is able to take in these X values and output a Y. That's supervised learning. Now, for unsupervised learning, let me clear this real quick. All you're given are the X values, and there are no Y values. None. So now we're trying to get insights just from the X, right? And so this, I guess you could still say it maps it out to a function, but this function isn't really mapping it to like a secret Y value. I guess you could kind of look at it that way, but to try to just keep it simple, basically we're no longer giving them the expected output labels. We're only giving them the input labels, and then it's up to the models to kind of make connections on their own. And this is usually through clustering. And we'll get into that, as we get deeper into the session. So if you didn't understand that, hopefully you understand by the end. Okay, so I thought that was a pretty quick explanation. So let's just jump straight in. So first things first, importing the data set. So we're not going to be working with the same data set as day one. So you're also open to have the do this on like Google Colab or Visual Studio. But I would recommend doing it on Kaggle's platform because that's what we'll probably be using the day of the Datathon. But anyways. To import the data set, first I'm going to do some important packages that we're going to need for today. Of course, import pandas as PD. You guys should be well familiar with that. Import numpy as NP. Um, import seaborn as SNS. Import matplot. Oops, matplotlib dot pyplot as PLT. And then this one is going to be a little bit different. So these you guys should be well familiar with. But this is where we're going to get our data set from today. So we're going to do from sklearn, which is scikit-learn, if you guys are unfamiliar. dot datasets import load iris. And this is going to be a data set, and we're going to get into it more a little bit. And actually, we're just going to, right here, we're just going to load it straight up. So iris is equal load iris. Um, and then we're going to convert it into a data frame. Um, and so we're going to do df is equal to pd.dataframe. And this is one way to like get like the scikit-learn data sets into pandas, since it's not always the most intuitive. So we're going to do iris.data, and then columns is equal to iris.feature names. Oops, iris.feature underscore names. Um, I think that's good. So run that. That should run. Give it a second. Um, oops, I accidentally. This has to be capital F in data frame. There we go. So that ran. That might take a second, and I'll let you guys catch up here. But basically, we're going to be using this Iris dataset, and actually, the first major thing that we're going to be doing today is exploring the data and cleaning to try to get you guys into the habit of always exploring and cleaning your data, because you're going to have to do that every single time you start with a new data set. So we're going to do that pretty quickly to give us an idea of what this data set really includes. And so yeah. We'll do that. And actually, I have one more import that I want you guys to import, which is more so if you're doing this on Kaggle, it just makes things look a lot nicer. Just import warnings, and then you're gonna want to do warnings dot simple filter action equal to ignore category is equal to future warning. Basically, if you're on Kaggle, uh, I don't know too much about the background, but I think it's using like a old Python version, I think 3.10, and then you get like some weird warnings that stuff is going to be deprecated pretty soon. And then there's probably ways to do that to update your notebook environment. But basically, what this will do is just make sure that those annoying warnings that look like errors are no longer pop up because that could be sometimes confusing. So let me run that. I think I got that right. Yeah. So. I'll just copy those. And so now we're going to start our dataset exploration and cleaning. So of course, first thing to do whenever you're given a dataset is df.head. And so let's see what this dataset has to offer. So this is the Iris dataset with Scikit-Learn. And basically, as you can see, we have four main features, which we have sepal length, sepal width, petal length, and petal width. And so this is going to be a dataset, and well, I'll show you more in a second. But it's going to be a wait. uh, Sorry. I got a little confused. Okay, this is gonna be a data set that's comprised of three different types of iris flowers. Um, and so right here, all we have are the features. We actually don't have the labels for each type of the flowers. We're gonna add that on in a little bit, but then later on the line or later down the line, we're gonna get rid of those labels because we're gonna want to do unsupervised learning, which means we don't even know what the labels are technically. Um, but we have sepal length, sepal width, and if you guys don't know what a sepal is, it was kind of confusing to me. But here, let me show you something really quickly. So sepal is kind of like the head of the flower, but it's like this middle thing, like that pokes out. If I go to images, it's like what this is. Okay, I'm pretty sure. Oh, or is it the thing under? It's I'm still not 100% sure. I think it might be like these petals under, or maybe the middle tube, might be the petals under. I don't know, but that, and then you guys know what petals are, obviously. So that should give you some context to what this stuff is, and then we have the length for all three of these in centimeters. So another thing you're going to want to do whenever you start exploring a data set is do df.shape. And as you can see here, we have 150 by 4, which means we have 150 rows, so it's not that big of a data set, and 4 columns, which we already knew by doing df.head. But yeah. And so now we're gonna want to, when we're cleaning the data set, and we're gonna get rid of this part later, but I think it would help you guys out a little bit. Also, I want to open the chat so I can see you guys in case you guys are saying anything. Okay. Um, we're gonna want to do df dot species. So we're creating a new column called species by doing this is equal to iris dot target. So this is from our original iris import from load iris. And basically what this is going to do is it's going to add a new column of the labels, right? So if I do df.head again, we could take a look at what that looks like. And as you can see, we have species. All these look like zeros right now. So if I actually do df species to show you that it's just not all zeros, I'll do value counts. These are the three different types of species we have, 0, 1, and 2. And they're not clearly labeled, but actually with some prior information that I wrote down about the data set, I'm going to actually make that a little bit easier to interpret for us. So copy what I have here. So we're going to take this data set and then we're going to change it to, and then we're going to species. We're going to take those values and then we're going to map them to basically different names. So here, just follow along. The first 0 means Setosa. 1 is, and I'm doing this within a dictionary, by the way. So I would do map, parenthesis, bracket, and then do this all inside the dictionary. Versicolor. Um, and then 2, ver, virginica. Sure. Don't know what those flowers actually look like. But okay, after we've done this, we can do another df.head, run that really quickly. And so now these species are actually mapped. And if I actually copy this again, um, out of this code portion here, and then do value counts, you guys can see that they're not 0, 1, 2 anymore. They've been mapped over to these new string features or labels, I should say. Okay. And one more thing that I wanted to do because if as you can see here, they make sure to say centimeter in the feature names. But I think that's kind of redundant and unnecessary. If we know that the features now, it's going to be easier to work with them if we change or if we rename those columns. So we're going to do a quick df.rename and then columns equals, and then we're gonna actually if we do a quick I would recommend you guys do the same. df.columns. We can see all of the column names here. And it's going to be a lot easier if I just copy this, paste it. So I did columns equal to a dictionary. And then if you guys were at the EDA one, this should be somewhat familiar to you, but we're just doing it again. So I'm just going to have it to where it's like underscores breaking it up, and I'm going to chop off the centimeter part. And I'm going to do this really quickly for all of them. So go ahead and follow along. So I'm just copying and then mapping it over to sepal width, petal length. Um, oops, actually, I did an extra. There you go. Is to petal. Oops, petal length. And then finally, really quickly, do that is equal to petal width. All right. And then if you remember you this one actually rename it. You have to do in place is equal to true or you reassign your data frame. Um but that will make sure that it actually gets saved. So run that really quickly. And now if we do df.columns again, you can see that all of those column names have changed. Okay. So again, this is like some normal stuff that you should always be doing, looking through your data. If you want column names to be standardized, which in this scenario they technically were standardized, but I wanted to fix them because I didn't like the way that they were. You do stuff like this, renaming, and we're gonna do a couple more things to clean the data set. Um, so I wanted to point out the shape of the data set again. It's 150 by 5. It was 150 by 4 before, but if you guys remember, we added that species column. So now it's 150 by 5. Um, and now, actually, I'm gonna do a quick df.describe. So if you guys remember what this does is it takes all of the numerical values in the data set and it gives you a little like common indicators for them or like important like statistics about them that you could possibly use. For example, pedal length goes from 1 to a max of 6.9, and here's like the median, and then like the standard deviation and the mean, if that's all, um, if that's all interesting. But I just wanted to remind you guys that that exists and to use that. But anyways, we're gonna do a quick value counts again. And we actually already kind of did it earlier, so maybe we don't need to, but I just want to do it really quickly so we could actually look that the species are evenly spread between all three of the types of labels. So that's pretty important to note. And usually, if the data set is imbalanced, you do stuff later down the line in consideration to that. But since it's balanced, I think we should be fine. And so now we're going to want to check for some null values. So let me even comment checking for null values. So if you guys remember, the way we do that is we do df.isNA, and if we run that, it's going to give us false slash true for everything, false for everything that isn't NA, and true for everything that is NA. And again, NA means you guys know what NA is. It's like basically a unknown value. And so the way that we actually interpret this is through dot sum. And as you can see, we have no missing values in any of our categories, which is pretty good. This data set's pretty small and cleaned up already since it's given to us by Scikit-Learn, so it makes sense. And so now we're going to also check for some duplicates. Um, and we do that by doing df.location, and then inside of df location brackets, we do df.duplicated. Run that really quickly, and we actually have one duplicate here, which is pretty surprising, but it makes sense. Like eventually, two of the same thing are gonna have like the same length through pedal width, if in a big enough data set, so it makes sense. And so actually the way to check what the other value is, because as you can see, it only says one of the duplicated values, and this is just saying that there's two that are the same, um, and this is one of them. But the way to see both of them is do keep is equal to true inside of df duplicated. Oops. Oh no, keep is equal to false. There we go. Sorry. Keep is equal to false, and then so these are the two matching or duplicated rows. And these are probably actually, like I said, two unique irises. But since what we're doing today is kind of using unsupervised learning to understand and visualize the data set better, I think that it's okay if we get rid of one of these, especially since if you think about it, it's gonna be like a point on top of each other that we don't really need. It will like lower the density at this point, which might affect the data set a little bit. Just looking into the future a little bit, but just to show you guys that or how to drop duplicates again and I don't think it's too necessary for today. This is how you do it. So we're gonna df is equal to, and then we're gonna do df dot drop duplicates, and then we're gonna want to do a reset index because basically whenever we drop the duplicates, the indexes will like shift or like there will be a missing index in there, so we're gonna have to reset that and do drop is equal to true, and this will get rid of that weird new column that it gives you whenever you reset the index. So if you do all this in one line, and you run that, should run smoothly. And now if we do df dot shape, you can see that we got rid of one of the duplicates. So now instead of 150 by 5, it's 149 by 5. Okay. Um, and so now I would say we've done most of the cleaning of the data set. We've checked for null values, we checked for duplicates. Um, we looked or we added the labels onto it and we've renamed some of the columns. And so now you could do more, but I don't think really it would be necessary. But if it was a bigger data set, you'd want to do more, but I think it's fine for now. So now we're going to visualize each one of the features really quickly. Um, and I know you guys are probably like, okay, get to the get to the what do you call this? Unsupervised learning already. What the heck is taking so long? Well, this is literally m more important. I'll be honest. Like and right now, sorry, I should probably not be talking over myself. Right now, what we're doing is we're gonna create a histogram for all of the feature distributions and as a visualization. So go ahead and just copy what I'm doing and we're gonna see what that looks like. Edge color is equal to black. This is just more of an aesthetic thing. The figure size that I have at the start is more of an aesthetic thing as well. It's not really needed, but it's nice. And then we'll do plt dot subtitle, which is like super title because we're going to see four different distributions. And we'll do feature distributions. Feature distributions. So that'll be the title. distributions. Um, but yeah, we will be getting to unsupervised learning, but again, it's really important to know your data set. So this is more important. And this is going to be what you're going to be spending most of your time on anyways. But if we do plot.show, as you can see, here are the distributions for every one of our features. They look pretty well. Sepal and sepal length and width are pretty normally distributed for the most part. Petal width and petal length actually seem like they kind of have like this U pattern to them, which is kind of interesting. Um, but important to note. And again, if you were gonna do more pre-processing and cleaning, you could do stuff like standardizing or normalizing. These if you don't really like them, and that actually might give you a better output in your machine learning model. But for today, we're not gonna go that far. Um, so that gives us the univariate analysis or just the singular feature analysis for every one of our features. Now we're going to be seeing comparisons between all the features. So the way we do that is SNS dot and um, I'll just scroll down here. SNS dot pair plot. And then we're going to put in our data frame, and then hue is going to be equal to the species column. Um, and this is going to be able to help us visualize what all the species and how they're distributed. And then this is also aesthetic stuff, but diagonal kind is KDE, so like the density graph, and I'll show you what that is in a little bit. And then corner is equal to true, again, aesthetic stuff, but I think it looks nice. And so we'll do plt.show. We show that off really quickly. It's going to take a little bit, but basically, if you guys remember pair plot from the first session, and let me zoom out here so you guys have a good visualization of the whole thing. It's going to map all of our features in on the X and Y axis, and now every one of these graphs basically shows us some relationships between like two of our features. So like it would be bivariate analysis technically. I don't know, but anyways, as you can see here, we have sepal length, sepal width, petal width, and you can go ahead and look at them. But as you can see, from the three species, which is what this hue did, it separated them by color. Um, there's some pretty, I would say, obvious distinctions between each species. They're already kind of in their own groups in a lot of these categories. I would say the only one that's not really like that is for sepal length, or like the sepal statistics, I guess. The correlation between sepal length and sepal width. The green and orange ones seem like they're kind of meshed together, but blue is obviously on its own. So some important stuff to look at, and then what this diagonal kind did, it turned all these diagonals into KDEs, and basically, what this diagonal is it's just petal width, like or like the singular features, but now it's showing you the distribution between the three species. So as you can see for petal width, um, Setosa seems to have really small petal width, while Varus color has like a mid petal width between 1 and 2 usually, and then Virginica has like the biggest petal width. And this distribution's a lot, smaller. You guys are able to read distributions, so you can look into this a little bit more afterwards if you're more interested. So I won't explain everything. As you can see here, the distributions for sepal width though they're all pretty similar. Um, Something that's pretty cool to note. Oh, sorry. I did not mean to zoom out more. I was already zoomed out like crazy. Okay. Okay. And so one last thing I'm going to make us do before we get onto the good stuff, which is the unsupervised learning, is just a quick correlation heat map. So we're going to do that real quick. So we'll do this by SNS heat map df.core. And then we're going to do numeric only is equal to true. This is something that I wanted to show you guys that I didn't show the first time. Um, sorry, inside of df.core as first value. Then we're going to do a comma. Annotation is equal to true. And if you remember what that does, that'll give us the numbers. And then CMAP is equal to cool warm. This is literally, again, an aesthetic thing, but I think it looks nice. And I wanted to show you guys some of the stuff. And then FMT is equal to dot to F. And this is like just for string formatting. Um, but if you're ever wondering, like, oh, like, how do you know all this stuff? Like inside of this function and like all these special like annotation, CMAP, FMT. How do you even find out about that? Um, I wanted to remind you guys that hit when your cursor is inside a function, do Shift plus Tab, and it will tell you what the function does. So these are the different variables that you could change. And if you're like, okay, that doesn't really help too much because I don't know what any of them do, if you scroll down, there's already a description on every one of the variables. So if you see FMT, string formatting code to use when adding annotations, CMap, uh, where's that at? CMap, did I skip it? I might have skipped it. Oh, it's up here. It's just a matplotlib color map. It's just changing the colors around. Annotation. If true, it writes the data inside of the cell, which you guys already knew. But again, I think that's something pretty important. And when you're first learning, it's gonna save you a ton of time from going back and forth between like the documentation or like searching it up. How do I change the color or how do I format the string inside? Remember that you could hit Shift Tab inside of a function and this stuff will pop up. At least on the Kaggle notebooks, and I think in most other IDEs as well. Um, but yeah, there's usually always some feature like that. Anyways, okay, then we're just gonna put a title on the plot. Let's grow those good habits now, because you don't want like untitled visualizations for when other people eventually look at your notebook. And then we'll do plt.show. And we run that really quickly, we can see the feature correlation matrix. So just a quick look over this thing really quickly. I know you guys understand how to probably read this from the first time I did, but in case you don't, um, the correlations are going to be from like -1 to 1. Um, 1 being that they're directly correlated. So as you can see, all these diagonal values are 1 because they're literally matching them with their own feature. Um, and -1 is they're negatively correlated, which means they're like complete opposite values, which means like if one value is high, the other value would be super low, basically. And this is a good way to understand the feature correlation for all the numerical values in your data set. I would always do this if you can. And just looking over it really quickly, we can see that petal width and petal length are highly correlated. So usually if there's a long petal, there's also a wide petal. Pretty pretty good stuff to know. In comparison to something like petal length and sepal width, pretty negatively correlated. So if there's a large petal length, usually the sepal width is smaller or vice versa. So that's kind of how you read correlation matrices like this. And obviously, this is like a really simple example. As stuff gets more complicated, it might be a little bit harder, but yeah. And all right. So that's it for cleaning your data and kind of like the setup to the actual unsupervised learning, which is the brunt of what we're going to be going over today. So if you guys have any questions about that, feel free to ask me. But I went pretty quick because a lot of that stuff we covered in our first workshop. So it should be somewhat familiar to you guys already. But okay, unsupervised learning time. And I forgot I had this description, so I didn't even have to explain it at the start. But what is unsupervised learning? Like what I explained at the start, there's no labeled data. So you're basically going to be giving all these input features, and you're going to be wanting to find patterns or structures within them. And then it's kind of up to the user to interpret that. Which makes unsupervised learning kind of one of the harder ones to um, understand in terms of interpretability, but the fact that that you're able to basically have no label features and just put a bunch of data inside of one of these unsupervised learning models, and then it's up to you to interpret it, makes it also super powerful for a lot of things um, or a lot of use cases, which I'll go over probably later. But anyways, actually, common use cases right here. So for clustering, oh wait, this isn't really like real life use cases, but common use cases for what unsupervised learning does is it clusters, it detects anomalies and dimensionality reduction. And we're going to be going over clustering and dimensionality reduction today. But anomaly detection is technically another part of unsupervised learning. Um, so yeah. And then I also have the types of unsupervised learning down here with some examples. We're going to be going over all of these today except for a Gaussian mixture models, which is like a density estimation. So feel free to look into that on your own. Um, but yeah. Without further ado, is there some? I feel like there's something else I kind of wanted to say about unsupervised learning. Oh, one thing about unsupervised learning, it that I like about so much as well is that it really tests your like data analyst skills. um, which is like your ability to actually like talk about or understand what's like the meaning behind the data. Again, kind of to what I said in a workshop a while back. Um, your own like of anyone could put the code in into the notebook and actually run it all, but it's really up to you to understand what that code means. And unsupervised is basically like that on steroids because the model isn't even going to tell you what the output is. It's up to you to like understand and kind of label that output on your own. Um, so it's like I really look at unsupervised learning as like the ultimate data analyst like flex, I guess, or like tool, or test is probably a better way to describe it. But anyways, let's jump right into it. So we're going to be starting with clustering, which is definitely the most interpretable and I would say the most useful type of unsupervised learning and what you should be doing 90% of the time when you're doing unsupervised learning. Um, and the most popular version of this actually is through k-means clustering. So let's go through that. Let me scroll down here. Okay, so I have some pros and cons of k-means clustering right here. First, some pros that it's fast and scalable and it's easy to interpret, which in a setting where you want to be interpreting what you're doing, it's pretty powerful because of that. Some cons though is it assumes spherical clusters, which I'll get to more a little bit, and it requires k-selection which basically means you have to choose how many clusters yourself. And there's actually strategies on what the best amount of clusters is, which I'll go over a little bit later today. But I want to point those out as some cons. So first, I'm gonna tell you guys to import a new library. So from sklearn.cluster, import k-means with the capital K and M. Okay, so run that. And that's how you import the k-means model. Um, and one thing that, if you guys remember, if I do a quick df.head, we're going to be doing unsupervised learning, but we have these um, like labels. So like that kind of defeats the point. So we're going to get rid of those labels or these labels really quickly, and then we'll just be left with these two. And we're actually going to store that into a different data set so we could compare it to the labels later on. So we're going to name that X, and we're going to do X is equal to our data frame dot drop, and then we're going to want to do columns is equal to um, bracket and then species because that is the column name that we're dropping. So run that really quickly, and X is technically a data frame, by the way. So if you do like X, I did a capital X, by the way. You could do a lowercase x, but just remember to stay consistent. If you do X dot head you could do that because it's technically a data frame. But as you can tell, there's no more species column. Okay, I'll get rid of that really quickly. Okay, so um, let's just jump straight into it. So this is how you train a k-means model. Um, it's really simple. All you have to do is k-means is equal to k-means and first of all, that might be a little confusing. This is just the naming convention or the variable, and this is what we imported from sklearn.cluster. And then in parentheses, the only thing you need to put into it, and there's other stuff you can put into it, but the only thing you need to is the amount of clusters you want it to make. And so we're gonna do n cluster is equal to 3 because we have some previous knowledge that three clusters, or we have three different species types in our data set. So three clusters intuitively, that's what we want to do. But if you say didn't really know how many clusters you want to do, I would test a bunch of different clusters and look at those separately. But just for this example, we're going to do k-means is equal to n clusters. Sorry. Oops. And clusters is equal to 3. Um, and then we're going to be making a new column in our data frame um, called cluster, and it's equal to k-means dot fit predict and then our input features. So basically all we're doing is mapping this new column in the data frame to whatever this k-means model predicts. And all you have to do is just run that. So just run that. Should be pretty quick because it's, again, a pretty fast model and our data set is pretty small. But if we do a quick df.head, let's see what that did. So now we have a new clusters or cluster um, column here. And if I do again like a df cluster, oops, cluster dot value count, value counts. As you can see, we have three different clusters, and these are the sizes of them. This is how it mapped them out. Um, and this is from the n cluster. So for example, if you did this slash like 4, if I just run that really quickly and then check this, now we have 4 clusters. But I'm gonna bring it back to 3, because we know that it's like there's 3 different main ones, and we're gonna compare that in a second. So now that you have your clusters, the best way to really see your clusters or understand them is to visualize them. And so let me show you how to do that right now. So we're going to want to do SNS dot scatter plot, and then x is equal to, and then we're gonna have to pick 2 features for x and y here, because we're going to be comparing how the X and Y's look to each other when depending on the different clusters. But since we have 4 different features, we have to kind of pick 2 so we could actually visualize it. So I'm going to pick sepal length as the first one, and then Y is equal to, oops, um, df sepal width. So we're just going to be looking at the sepal stuff. And if you remember from earlier, actually, this stuff was pretty tied in together. So this is probably one of the better ones to test out, um, to see if it really did a good job. And then hue, this is the most important part, is df cluster, which is the new clusters that we made. Um, I just cluster, right? Yeah, just cluster. And then this is just aesthetic again. I want to do palette is equal to, you don't have to do this, but I want to. Viridis. Just makes it look better. And of course, we're gonna need a plot dot title. And then we'll name this K means clustering of iris dataset. Okay, and we'll do plt dot show. So if we run that really quickly, as you can see, we can visualize the clusters. So all these different points represent a row in our data set, and then they're all mapped on sepal length and sepal width. And you could see how k-means clustered all of it. Obviously, it took in more data than just sepal length and sepal width. Um, but here are the 3 different clusters that it came up with: 0, 1, and 2. And actually, I probably should do that. What you can also do is use the original data set. Um, Oh, wait. I think we could do that. Okay, copy this completely, put it down here, and instead of use df cluster, we'll do species. Since we actually have the correct labels, and you can't always do this, so this is probably a bad habit to show, but since we do have the correct labels, we can see what the correct labels actually are. Um, so here are the correct labels. I wish they were the same color. That's kind of annoying. But anyways, um, so this is what our k-means predicted, and this is what they actually are. So as you can see, it did a great job. Um, they look really similar to each other. Um, as you can see, I would say there's in here they're tied in a little bit more, and they're kind of more split up down the middle here. But other than that, it completely got this cluster correct, and they basically got these 2 correct as well. So that's one cool thing you could do. If you have the correct labels, you could like visualize how the model is performing. But that won't always be the case, like I said. So don't worry about that too much. But yeah, so that's k-means clustering. We're gonna come back to how to pick the optimal amount of K clusters, or K groups, I guess. Yeah, I guess N clusters is the right name. A little bit later, and but this is going to be it for now for visualization. This is one of the most important types of clustering for unsupervised learning, by the way. Okay, so now we're going to be talking about hierarchical clustering. Just like had a stroke trying to say that. And this one is a little bit harder to interpret, and I'm gonna do my best. But to be fair, I don't know if I'm gonna do a great job. So if you don't understand, I completely understand, and I would, if I were you, go out and actually look at what, like a YouTube video. One I would recommend is like this person called StatQuest. But look up a YouTube video what hierarchical clustering actually is. But I'll try my best. Um, But let's get into it. So, some pros is there's no need to predefine a k number of groups, which is great. Um, and it creates a dendrogram, which is a visual hierarchy, and we're going to print that out later so you can see what that actually is. And some cons is it's computationally expensive, which means it takes longer to run a lot of the time, and especially on larger data sets. And it's sensitive to noise and outliers. Um, so basically performs not as good. And so let me explain what a dendrogram is really quickly if you haven't already, and I would look into it because if you haven't, because it's basically the whole idea of what hierarchical clustering is. But think of it as kind of like a tree. There's different types of hierarchical clustering, and I'm not going to get into all of them right now, but this is the best way that I could kind of tell you how to do it. So just imagine we have features A, B, and C, and realistically, these are going to be more like your rows in your data set. Um, and so what hierarchical clustering is going to do is it's going to take the distance between your rows, which could be from a multitude of things, and it could be different the way it takes it in. But basically, it'll take the distance between the rows, um, or yeah, like the different rows in the data set. And what it'll do is uh the ones closer together, it'll match them. So basically, it'll it'll turn AB, let's say AB is closer to each other than like BC or AC. So this will turn into A comma B and then C, right? And then now this will be one group and this is another group, and now it'll run that again, and then obviously it can only go into one A, B, and C altogether. And so what this does is it gives you an idea of what similar rows are in the data set through something called a dendrogram. And basically, a dendrogram is kind of like this tree thing that I drew out, but obviously, this is like not a great way to visualize it. Another way I could visualize like this, X, 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 X. These are all different rows, and it's usually these two first, and then okay, then these two, and then eventually it matches up like this. That's actually like the correct visualization for it, but I thought this example would be better. So basically, that's what hierarchical clustering does, is it groups smaller stuff together first, and with this whole idea of basically, if stuff is similar, put it together, cluster them together, and then kind of go up in this hierarchy depending on what the next match would be. Okay, so let me clear that off really quickly. And again, if you didn't understand that, I don't blame you. But go check it out yourself, I would say. Okay, so what we're gonna use for this is actually SciPy. So I'm gonna do from SciPy, and the reason we're doing it from SciPy is um, I don't think um, I don't think sklearn has a good way to visualize this in comparison to SciPy, so we're just doing it from SciPy. But from SciPy cluster.hierarchy import dendrogram and linkage. Okay. And I don't think I misspelled anything. I did misspell something. Dendrogram, I misspelled it. How do you spell it? Dendrogram. Okay, good to know. I'll add one more piece of code here. Okay, and so the way that we create this hierarchical cluster is through, I'm gonna name it Z. Z is equal to linkage. And then we're gonna put in our X, which if you remember are our input features, and then method is equal to ward. There's a ton of different methods, and again, if I do Shift Tab really quickly, oops, and we scroll down, you could see it actually explains what the different methods are. We have single, complete, average, weighted, centroid, which I think is actually probably a good one that we might try. Um, and then we're going to be doing well, let's do centroid for this one, but ward is another one that I was planning on doing, but I think centroid is the one I'm most familiar with. So look into those. It says that there. I'm not going to explain all of them, and they're pretty mathy. But anyways, this is how it's going to choose that hierarchy and how to group things together. So let's run that really quickly. And then using this dendrogram that we just imported, we're going to do input Z. which is our hierarchical cluster model. And then we're going to do the labels is equal to df.index. And then this part is kind of irrelevant because it's not really readable, so I won't even try to confuse you with that. But basically, we're just putting in the labels and the z value, and the labels are the indexes because it's the numbers or the specific index of the row. And I'm going to show you what that means in a second, but you're not going to be able to see it anyways. So I don't think it really matters. Um, hierarchical clustering dendrogram. Dendrogram, dendrogram. Okay, and we'll do a quick plt.show. So we run that really quickly, and here it is. So kind of like the picture that I drew earlier, except as you can tell, it's a lot more complicated because we have 150 rows. So instead of just doing like the A, B, C, we're doing like 1, 2, all the way up to 150. And honestly, we have a small data set, so imagine a bigger one. But anyways, um, and basically these down here are the index numbers. That's why I didn't even try to like go into that too much. You can't read those. There's actually different ways to interpret this, but this visualization is good for understanding basically how it works. So as you can see, it actually split them up into like two main groups right here on its own. And so you could kind of tell from the coloring that it did that. We're not gonna go into too much on how to really understand and like show through code which indexes are which. Um, it's actually all stored in the z value, or which indexes are which I guess groups is what I'm trying to say. Like kind of similar to k-means up here. Let me get rid of this on the screen. K-means we were able to visualize yeah, the clusters. I'm not so we're not gonna go take that extra step to see which indexes are part of each cluster, but you can, and it's not too hard. But this should give you a general idea of what this is, okay? Or from what hierarchical clustering is. So now we're gonna move on. And I had this picture is massive. It was not this massive, but I showed it earlier or put imported it earlier. Okay. At the very top here, you can barely see it. We're gonna move on to density-based spatial clustering of applications with noise. Which is like, wow, that's a mouthful. But it's shortened to dbScan. So you could call it that. dbScan. And you could actually kind of tell from the name what this does. So it clusters based on density. Okay? And I actually found this picture online that shows it beautifully. So usually k-means checks like the nearest stuff in like from like the center of a group but what dbScan is going to do is it's instead going to look to the closest in its like each feature's vicinity and match that to a group instead of like again, let's say you pick two clusters, it's going to be like, okay, so this is one group because we're on the right side, this is one group on the left side. And another cool visualization of this, dbScan is on the right. This is like a more densely packed. Um, and this is like more tightly packed as you can tell, but then k-means kind of struggles with stuff like this and it'll end up like chopping it down the middle basically. um and I had the pros and cons here, but going back to k-means actually really quickly, I said one of the cons was is it assumes spherical clusters, and you could kind of tell from these pictures what that is. The two spheres here are like this, and then like this, and then like if I scroll down, um, like you could see them, but this top cluster and this bottom one. But dbScan, it does it based off of density, which is pretty cool. So some pros is it identifies arbitrary shaped clusters instead of like k-means, or unlike k-means, it's able to pick up on like these dense structures. Um, and it handles noise and outliers pretty well. And we're gonna to look at that in a second. Um, but some cons is it's pretty sensitive to its parameters, and you kind of have to like pick and choose the right parameters for it to really work. And there's probably strategies out there on what parameters or how to fine tune those parameters, but I don't know too much about that. And it also struggles with varying densities. So let's say something is really tightly packed, but then this group is like maybe not as tightly packed and all over the place. It's gonna like try to group them up in a certain type of way, and it's gonna struggle. And so let's get into it. So what we're gonna have to import is from sklearn.cluster, import dbscan. And then I could run that. Or yeah, I'll just run that. And then some the code to actually make the dbScan model is dbScan is equal to dbScan. And then here are the two um parameters that it's going to be sensitive to, and I'm going to explain them right here in a second. But eps, which actually stands for as epsilon, and we're going to set that to zero point 0.5, and then min samples is equal to 5. So to really understand these parameters, and we're actually going to do a fit to our data set just straight up. We're not going to just do it on a separate line. We'll do it right there. Um, but basically, um, to really explain or understand how this works, you have to kind of look into the math of how it works. But conceptually, I could kind of explain it really quickly. So epsilon is going to be the maximum distance between the 2 points. And this scenario is going to be zero point 0.5. That's what we set it to. So for 2 points to be considered part of a cluster, they have to be zero point 0.5 point away from each other, which I don't know actually in this scenario what that epsilon represents. It's not like inches or something. But it's a number, and basically there's like a minimum distance that they have to be from each other, right? And then um, min samples is how many samples do you want to consider for something to be considered a cluster. So if say there's like four things tightly packed, but those are only four things, that doesn't necessarily mean it's a cluster. Maybe those samples were specifically tightly packed, but then it's part of this bigger cluster, or actually there's two different clusters that it's part of. Stuff like that. So like the minimum samples is basically how many samples do we need for something to be considered a cluster. And so one last thing that I want to do here before we run this. And again, if your best friend is going to be Shift Tab here, I'm pretty sure explains that in here perfectly. Yeah, exactly. Epsilon, the maximum distance between. I probably should have just read straight off of this instead of explaining it, but anyways. And one more thing we're going to do is we're going to create a new column in our data frame called dbScan cluster. So this can be similar to the k-means cluster, but now we're going to be doing it for the dbScan ones. And then it's going to be equal to dbScan labels underscore. Okay. So run that really quickly. Should take a little bit. It's not the quickest model necessarily, so give it a second. It's still running actually. Wow. Jeez. Is it still running? I can't tell. Okay, anyways, I'm gonna continue. Okay, it just finished running. Wow, that took a lot longer than I thought. Maybe that's another con is that it's computationally expensive because that shouldn't have taken that long. Anyways, now we're gonna visualize those clusters that it made. Um, how did we get dbScan? Sorry. Oh, it's from this thing up here. Did you still want clarification on that? I just missed that right now, I think. Um, just let me know. No? Okay. All good then. Okay, and so now we're gonna visualize those clusters similar to what we did in um, for k-means. So we're gonna do that through a scatter plot. So SNS scatter plot, and then we're gonna do x is equal to, and again, with this one we're gonna have to be looking at specific features within the data frame, um, because we cluster them into groups, and so we have to basically compare them in that way. I kind of already explained it earlier with um, the k-means. So we're going to use sepal length and sepal width again. So x we're going to set to sepal length, and then y is equal to sepal width. Oops, df that's sepal width. And then the most important part is going to be the hue, which is actually going to show us what the clusters are. And then this is going to be dbScan cluster. Okay. And again, for the aesthetic, I'm going to do the palette. Palette. Um, I spelled that wrong. It's equal to, I think the one I like is Bird or something. I have it actually written down over here. Give me a second. I'm just gonna paste it. What is it? Viridis. I don't know how to say it. Anyways, and then we're gonna do a plot title real quick. Again, these are good habits that you should be building. Always have a title for your visualizations, or else, you might look at it a month down the line and you're like, what the heck does this even show? Um, and then, so I title it DB scan clustering of iris dataset. And we'll do a plt.show. Show that really quickly. And here we go. Um, Technically we have three different clusters, but actually, when this DB scan runs, the -1 outputs are the outliers. So this is one of the pros of dbScan, is it identifies outliers. Um, and it does this by obviously outliers are not densely packed with everything else. So it's able to identify them in that way. Um, but it also, in our scenario here, this isn't actually what the iris dataset looks like. K-means actually did a way better job of showing it. Just because these two are really similar. So when dbScan looked at it, it was like, okay, these are densely packed. So this must be one cluster, and this must be one cluster. Okay. So in some scenarios, there's some trade-offs between dbScan and k-means, but that should give you an idea of how it kind of works. But yeah, so -1 means that they're outliers, which is super useful, and k-means actually struggles to identify outliers. And then it put them into these two different clusters. And if we play around with these variables to show that their sensitivity, for example, if we do like 0.1 for epsilon, um, and then like minimum samples keep it the same, all of a sudden everything is an outlier because nothing's close enough. Or if we do like 1 for epsilon and minimum samples 5, all of a sudden there's no more outlier. These aren't considered outliers anymore, and now there's two different ones. If we like increase the minimum samples to 10 and run it again, oh, actually that should it pretty well. Let's say epsilon is like 2. Okay, I'll probably show what I'm talking about better. All of a sudden everything is just one cluster, right? So that's what I was kind of saying when I meant like these variables are pretty sensitive. So definitely try stuff out and see what kind of makes the most sense intuitively when you're testing. And there's probably, again, like I said, out there ways to fine tune them in the right ways. Um, but it's probably also different for every data set. So that's dbScan. And so that basically finishes up on our clustering. We went over hierarchical clustering, dbScan, and k-means, which I would say are like the three most popular ones. K-means and dbScan being more popular. Um, but we're gonna go over a little bit more them again when we're doing the evaluation. But now we're gonna move on to dimensionality reduction. And so, yeah, let me take a sip of water real quick. So, what is dimensionality reduction? It is the process of reducing the number of feature variables in a data set while preserving as much important information as possible, which is super useful for a ton of reasons. First, I have them listed down here. It removes noise and redundancy by kind of grouping them up into one feature. It improves the computational efficiency because instead of having like say like 7 features in the data set, if we put them down into 2 features, obviously it's going to be easier to run. It enhances visualization. For example, if our data frame actually has 4 different features, if we put them all down into two, we wouldn't have to do stuff like look at the sepal length and sepal width. We could just use the 2 features that it made and then visualize those. So imagine stuff with a ton of features. It'll be great to visualize or a great visualization tool. And then it avoids this curse of dimensionality, where basically too many features can create or make models less effective. Like for example, if you throw in like 1,000 features into a model, that doesn't mean it's going to be better than a model with like 50 features. Actually, a lot of the time it's going to be worse because it tries to take into account all of these different features, and it's not able to, like maximize its or minimize its like loss or cost as effectively as possible. Um, so that's kind of what this curse of dimensionality is. And so I would say this is more, I look at it and it's considered unsupervised learning, but I uh, consider it more of a data preparation tool. for like machine learning models. And it's also good for insights because of the visualization and like seeing how kind of features correlate with each other. But because this doesn't really need to only be done on unlabeled data. This you could also do this for labeled data sets, just to just make it easier for the model to read. And that's actually something at a higher level is done all the time. Dimensionality reduction is always done because with these huge data sets, the models are less effective when there's so many features. So. Like if you guys ever get a job in data science, I'm pretty sure, and from what I've heard, stuff like PCA, which is what we're gonna go over today, is super popular. But anyways, and let's get into it. So the first type of dimensionality reduction I'm gonna talk about is PCA, and this is like the most important one, or not most popular one, from what I've seen. And so, some pros about it is it reduces complexity while retaining information, which is exactly what we want, and it improves model performance and visualization, which is kind of the stuff we went over above. The cons with dimensionality reduction in general is like that stuff is helpful when you're trying to visualize and train models, but now that all your features are kind of clumped into one, it kind of loses its interpretability, which is why it's more of like a um unsupervised model tool, I would say, because without labels, the stuff's kind of hard to interpret anyways. But anyways, it loses its interpretability because all of these features got kind of numbed down into one, and it assumes linearity and requires standardization. And I'll explain that more in a little bit. But basically, it just assumes a bunch of the features are linearly correlated, and standardization is needed because if you have like one feature that ranges from like 0 to 1 million and one that goes from 0 to 1, um, it's gonna be kind of hard to combine them for PCA specifically. So let me show this off. So the first thing we're gonna want to import is sk from sklearn dot decomposition import capital PCA. Hopefully I spelled decomposition right. I did. Nice. And to basically create the model, we're going to do PCA is equal to PCA and components. And that's the most important part, which is the amount of variables you want to reduce it down to. Components, that's how you spell it. And we're gonna reduce our data set down to two because basically that'll make it easier to interpret. Um, or easier to visualize on like a graph. And then we're gonna want to train that. And so we're going to call this xPCA is equal to PCA dot fit transform X, which is our training data. So run that really quickly. Went by pretty quick. And so now that we have these two new features inside of xPCA, I will be putting that inside of our data frame so we could actually use it. So we will be doing that by PCA1. So the first one we're going to call PCA1, the first variable, and then we're going to have to segment off the XPCA. And so we do that by doing a little bit of this, okay? And then DF is equal to PCA2, and then is equal to, and I'll say it out loud. So XPCA bracket, colon, comma, and then this one's going to be 1 actually. So this is going to get the first column, and one is going to get the second column or second row of features. Um, and so we're going to store that into our data frame so we could run that really quickly. And so now we could actually visualize this. So how do we do that? We're going to do plt.figure. Actually, well, this is actually just modifying the figure size. We don't have to do this part. We'll do a SNS scatter plot, our favorite. So now instead of being forced to set the X and the Y as specific features in the data set, now we've dumbed the data set down into two features. So let's take a look at it. So we can do X is equal to DF PCA1, and then Y is equal to DF PCA2. So these are like the two features we just created. And then uh well we'll do a hue right now. I'm gonna comment this out actually. Um after the first one, because this isn't really gonna be normally what we see in unsupervised learning. But since we have the label here, we might as well take a look at it. And palette, this is just another aesthetic thing. I'm gonna change it to cool warm. I might just do cool warm because I actually like the way that this looks a lot. Oh, sorry, I forgot to put a title. PLT dot title, um, PCA visualization of iris dataset, and then plt.show. And if you guys are wondering what plt.show does, it gets rid of this ugly axis thing. Okay, Um, so here it is. As you can see, if we get all of our data set into two features and then we plot it on the X and Y axis, this is what it looks like. Um, and this is super useful. For ours, since we know what the original species is, you could actually see how they're different from each other. But again, we lost interpretability. So what does this really mean? Who knows? Just because it's on the left side, I don't really know what that means, but obviously that these are a lot different from these in some ways. Um, but if the goal is to make the most efficient machine learning model, and this is why it's so popular in the industry, and the interpretability is up to like the data analyst to figure out down the line. It doesn't really matter right now. But if we're making a machine learning model as effective as possible, we want to get those features reduced to help do that. And so that's why PCA is so popular. And so again, it's not only for unsupervised, but it is technically a unsupervised model, the PCA model. But yeah, so this is pretty cool. And then if I actually get rid of hue, just to see what this would map the features out as, here we go. Um, oh, the palette, yeah, technically I'm getting the small error. But anyways, this is what it would look like if it was really unsupervised. And you get to visualize like say if we didn't know that the data set had three different species, right? And you're not going to if you're really given an unsupervised data set. I'd look at this PCA visualization and I'd be like, okay, obviously we have two different clusters. This is amazing. I could take these values over here and I could try to cluster them together and see what that really means, and then take these over here and cluster that together and see what that really means. Obviously, in kind of like from an omniscient perspective, we know that these are actually two different species, so I would be doing harm. But as you can tell, this is a really strong visualization tool because of stuff like this. In comparison to like doing feature by feature comparisons, this is like a whole data set comparison into or visualized. But anyways, I'm gonna put that hue back actually because um, it looks good and it gives you an idea of how it does its job. And as you can tell, I would have been somewhat accurate. I would have known that these are paired together. But anyways, so that's basically, I was taking my time there to kind of explain why we do PCA and why it's so effective, um, or like dimensionality reduction. But now we could just move on a little bit quicker. So this is another type of dimensionality reduction. It's called T-distributed stochastic neighbor embeddings. God, why do all these unsupervised models have such long names? But this one is just another type of dimensionality reduction. Some pros of this one though is it's great for high dimensional data visualization, and works well with nonlinear data, unlike PCA. So if the a lot of the data isn't linearly correlated, it doesn't have to be standardized. You could just throw it straight up into this thing. The only downside is it's computationally expensive and it's non-deterministic, which means every time you run it, technically you can get a different answer. Um, Unless you set a random state, which is what I'm going to show today, but that's just like a way to make it to where specific ways are always like acting the same way, but it's non-deterministic. Anyways. So how do we do that? So we're gonna import from sklearn dot manifold, import capital, oops, I can't spell, tsne. Okay, and then we're gonna set it. I should probably run that actually. There we go. Um, tsne is equal to tsne And then we're going to do n components is equal to 2 and random state. So technically you don't need this random state, but it just means every time you run it, it's going to be different, which might be a little annoying. So this random state basically makes sure that whenever you have to rerun the notebook or something or rerun the model, that it stuff stays the same. And we're actually going to fit it right away. So we're going to do x tsne is equal to tsne um, dot fit transform. And then we're going to throw an X, which is our feature labels. So again, it has n components just like PCA. It's basically it's really similar to PCA except it's better for nonlinear data. And so we're gonna do kind of like the same thing. I'm gonna run that really quickly. Kind of the same thing that we did earlier, except now we're gonna do TSNE. So there's gonna be df is equal to TSNE1 or a column TSNE1 is equal to now this x TSNE, and then we're gonna have to do some. I forgot what this is called. Like when you do this stuff in Python. Um, I always I'm always bad about remembering what it's called. So we're gonna do colon comma 0, and then df TSNE2 is equal to x tsne. Well, I think it's like splicing or something. That's what it's called, right? Um, colon comma 1. Okay, so that's how we get our two different sets of features. Run that really quickly. So we store that in the data frame, and now we could just visualize it. So again, with the scatter plot, and actually to make our lives easier, let me grab this up here. Okay, just grab this code that we had. It's because it's really similar. And then instead of these DFPCAs, we're just gonna change it out for TSNE1 and TSNE2. And then this is gonna be the TSNE visualization of the iris dataset. And I'll keep it cool warm as the vibe. And here we go. So again, a good visualization of the data set. As you can tell, it's different from PCA because it assumes this non-linearity. Um, and also, um, it really segments, like when you visualize it, it really does segment off these different groups, which is super cool. And if we had like a bigger data set, we would be able to show the why it's better for high dimensional data visualization. Um, but for now, since we have a small data set, it's just kind of made these two groups. But like say we had like a bunch of features, it would like probably have a bunch of different groups, and then from that we could kind of interpret it, right? And to kind of give you guys an example, um, of basically, and I'm gonna go over this again at the end, but visualizations like this are so useful for unsupervised learning because in our case, we can assume that these two different groups, for example, like if we didn't have like the species already told to us, are like two different types of irises, because all we were given is a bunch of iris data, and so now that we see this, okay, this iris is obviously different from that iris. And then we would probably assume two groups, even though we in reality it'd be three groups. But there's probably other ways to find out those differences, which is super cool. But in like scenarios where and a possible application of unsupervised learning is if you're given like a bunch of customer sales data, um, and like you put that onto like an unsupervised model. Like TSNE, and then you run it and you visualize it, it'll group up customers, right? And then from there, you go in and you're like, okay, this is a group of customers that of high buyers. Let me go in, like after like seeing what all of this data means. Um, Okay, I think this is the group of high buyers. So let me go into them and give them like some discounts. These are the people who barely visit the website, so maybe we'll send them more emails. So this is like some applications of unsupervised learning to show kind of like what the whole point of this stuff is. It's like from this point up to the person to try to interpret. And then you kind of have to go deeper into actually really interpret these visualizations. Um, so yeah. So let me show again without the hue what it'd look like just as an example. And so I would probably assume, okay, so we have two data sets, right? But actually, it almost looks like three data sets, right? You could kind of make three different circles from this. So I'm like, okay, there's obviously like a kind of a line going on there. And then if we actually take that into consideration, this is insanely accurate. And like it really represents the data super well. So let me put that back. Q is equal to um, df species. Oh, forgot the comma. Okay. Alrighty. So yeah, super cool, super cool. So that should give you an idea of dimensionality reduction. Again, that shouldn't only be focused on as an unsupervised model. It can be used as a tool for other models. It makes them a lot easier to train, but it loses that interpretability that we kind of want sometimes. So, is there anything else I wanted to say with that? Oh, and I wanted to run a last df dot columns to kind of show these different columns that we made. And actually, if I do a quick df dot head, so you could kind of see them. So here you go. Again, these values not interpretable. Like, what do you mean negative 21? What do you mean PCA for row one is 0.319? Um, who knows? And if I mean, you probably can interpret them if you like, really get into the statistics of how these models work. But again, like just from like a data analyst science standpoint, we don't really it loses interpretability, as you can tell, but it does a pretty effective job, as you can tell as well. Well, okay. So that is step number two, which is I went over dimensionality reduction and um, clustering for unsupervised models. There's also anomaly detection, and there's also one that we didn't go over today. I forgot what the name of it was. If I go up to the top really quickly, density estimation. I don't know that much about that. If I had to assume just from the name though, we would see like how densely packed clusters are, kind of similar to DV scan, but probably in like a little bit of a different way. But feel free to look into more unsupervised methods later on. But I feel like these are the main ones I really wanted to touch on today. So now we're gonna go over pretty quickly evaluating these unsupervised models. Um, and there's some like clear cut ways, and there's like some more up to the person ways to evaluate the models. But let's go over them. So silhouette score is a big one. And this is probably if you're clustering with your models, this is probably like the main way you should interpret them. Um, and so this is how it works. It measures cohesion and separation, which is how close the data points are within the same cluster and how far apart the data points are from the same cluster. Basically, how well did we cluster the stuff together? And so it's going to be on a range from 1 to negative 1. 1 meaning the clusters are well separated and super dense, or 0 being like there's overlapping clusters and stuff is like kind of ambiguous, and negative 1 is just straight up like bad clustering and points are in the wrong clusters. So if we let's try this with our k-means from earlier. So the way we're going to do this is going to be from sklearn.metrics import sil who at score underscore score. Um, and then I'm going to run that and actually have some code under it. And so this score is going to be silhouette score. Um, God, why is that such a hard word to spell, man? Silhouette score. And then we're gonna put our input features and then the column that actually has our clustering um, in it. And then from there, we're gonna print out what that silhouette score is. So we'll do like a quick F string to show that off. Silhouette score for K means, um, and I don't have to. I did a F string, so I don't have to do that. And then it's gonna be score. Okay. So if we run this really quickly, so this is our score for k-means. It's a 0.55, which means we did a pretty decent job of clustering them together, which is super cool. And you could also do this for the DB scan. I'm not going to go over it, but you could also get the silhouette score for the DB scan or any clustering algorithm that you have. Um, but yeah, so that gives you a good idea, and this is really how you look at like clustering evaluation. This is like the main way. This is like the accuracy of a classification model, but now it's the accuracy of your clustering. Um, so that's pretty cool. And so now we're gonna go over the elbow method. And this is for specifically for k-means and how to choose how many k clusters you should use. So in an actual data set, we're not going to really know, we're not going to have labels to our features. So we're not going to know how many clusters to put them in. Obviously, for our data set that we're working on today, we knew the different species, so that wasn't the case. But normally you don't. So you're going to be kind of confused on how to pick how many clusters and if it's actually represented. And this is a method on how to do that actually. It's called the elbow method. And as I say here, a good method in finding
Call has been
the
forwarded to
best
voicemail.
number of k groups for k means. Let me that really good. Anyways, so let's get into it. So first of all, we're gonna have these things called inertia values, and we're gonna store it. It's gonna be an empty um, list for now, and then we're gonna have k values, right? So basically, the way the elbow method works, I should probably explain that before we get into it, is it's gonna test a bunch of different k values for k means to see what works best with your data set. And then it does that by creating these inertia values based on the k values you give it. And so these k values is going to be a range from 1 to 10. And if you're kind of unfamiliar with Python, um, this is how you do that. So this is basically the same thing if I commented out as a list of like 1 to up to 10. That's all it is. But anyways, so for k and k values, um, this is what we're gonna do. So for everything, for every number in k values, 1 to 10, we're gonna do k means is equal to um the k means we had from earlier, and then or it's technically a new k means model. N cluster is equal to k. So it's like equal to the value originally is gonna be 1, going all the way up to 10, and then a random state. We don't really need to do that. We can just keep it the way it is. Okay. So, and then k means dot fit x. So we're going to be fitting every one of these values to our features, and then or every one of these models, I should say, to our features, and then we're going to do inertia values dot append, and then k means actually has something called inertia, which is a type of score. And if you want to know more about what inertia means, I actually don't have like a really super good. Like we're gonna look at the visualization of it in a second, so it gives you an idea. But I don't have a good way to really describe how they arrive at that, so I would look into it. But basically, for every time, for every model, we're going to be storing these inertia values, right? So let's run that really quickly. And thankfully, this runs pretty quickly because, like I said, k-means is a pretty lightweight model. So it doesn't really take that long to run. So running a new model 10 times and fitting it to our data was like almost instant right there. Um, and so now, how do we actually interpret this? We're going to have to plot it. So we'll do plt.plot, and then so we're going to take the k values that we have, which is this list from 1 to 10, the inertia values, and this is, by the way, this is making it on the x and y axis. So k value is going to be x, and I should probably do that here. X is equal to k values. Oops, accidentally. Right, x is equal to k values. Y is equal to inertia values. Um, and then this is like for interpretability. But marker is equal to an O, and I'll show what this is in a second. And also line style um is equal to, and then we're gonna do two hyphens. Okay, so just copy that, and I'll show what that did in a second. Um, and then we're gonna want to plot our labels because they're actually not gonna give us really good labels. So we'll do plt.x label, and the x is gonna be the number of clusters, okay, and then plt.y label is equal to number, oh no, the inertia values. Inertia, and inertia is a sum. I actually wrote it down here. I should have known that. A sum of square distances. Okay. Um, so I'm guessing this is a sum of square differences between the different clusters. Again, look into inertia more if you're interested in how this really works. But we're using this as a tool, so you don't really need to know too much. And then I'm gonna title our plot. It's plt.title. Sorry. I'm gonna title it elbow method for optimal K. So this is how we find the optimal K. And then we'll do a quick plt.show. And let's see what this gives us. Oh, I messed something up. Oh, inertial values. Oops. It's inertia values. Uh-oh. What else? Unexpected keyword got unexpected argument X. I accidentally. Oh, I think these I shouldn't be doing X and Y. Sorry. Don't copy. Just do K values and inertia values. I think I messed it up because I think I'm thinking of like the pandas, and so the mapping is a little bit different for this. I could actually do Shift Tab and look how that works actually. Um. Oh, so this is wait plot X. Whatever. I'm not gonna take too much time looking at this, but basically just do K values, inertia values, and then marker and line style. And now we should run it. And so here we go. We got a graph, okay? And so what does this mean? Down here, I kind of say how to interpret this graph and how do we pick the optimal K for our K means given our data set. So the elbow point is where the inertia stops decreasing sharply. Okay, that's the most important part. Before the elbow, there should be a huge drop, which is what we see. And then after the elbow, there's a small decrease in inertia, which means overfitting, if you guys remember that. And so basically, this is why it's called the elbow method. It should look kind of like this elbow angle. And so from that, as you can see, and also I'll go get to that in a second. But anyways, two is where I would say the biggest changes. It's two to three. I would either pick two or three for the most optimal K, because that's where it starts straightening out. And it's basically if you think about like in like calculus, the second derivative, what are those called? Basically those inflection points. If you think of like an inflection point, we're basically trying to see what the inflection point is, where it, like the second derivative technically hits zero if we're really gonna get mathy about it. Um, and like that's where the optimal K is. Um, So again, it's either two or three. I would try both in this scenario because this is where it kind of strains out, and then this strains out more, and then everything after this is pretty straight. But anyways, I said in our example, two or three cluster seems good. And as you can see, this is pretty accurate because if you guys remember, we have three different species. So we would probably test two or three, see which one worked best for K means. But um, this elbow method works. And there's actually other methods you could use to pick the the best amount of clusters you should use or yeah, input, but this is like the most popular, I'm pretty sure. But you can feel free to look into those. Let me take a sip of water really quick. But yeah, so that was the elbow method. That was for picking the optimal K. Um, is there anything else I want to say about that? I think that's it. Okay, so hopefully you guys understand that. So now technically this is we should have done this before. This isn't really a evaluation method. This is kind of like a but while we're making the model method, we do this and then pick which one is the best. But anyways, uh, so other evaluation metrics not gone over today. Obviously, I kind of went over the workshop time. Um, so I don't want to spend too much more time on evaluation metrics. But here are some important ones that I have noted, and I'm also gonna when I post the YouTube video, I'll have this notebook in the description. Um, so if you guys don't write this down right now, but you want to look back at it, um, I'm gonna have it there, okay? But anyways, so other evaluation metrics not gone over today. We have some internal metrics. So this measures how well the algorithm. Oops, I didn't mean to do that. How well the algorithm clusters the data itself. And we saw this through the silhouette score, but there's also another popular one called Davies-Bouldin Index, called DBI, and inertia actually. Um, then we have some external metrics, which is compare clusters to known labels if available. So in this scenario, we did know the labels, and so that's one way to evaluate actually if you do know the labels to see how well we're clustering things together. Um, and so in this scenario, it looks like two main groups that I kind of argued that it could be interpreted as three. So this did an amazing. Um, and there's actually tools to help you do that too. ARI, NMI, V-measure, cluster purity. I'll be honest, I'm not an expert on any of those, but I searched them up, and apparently those are some popular ones. Um, And then we have stability and robustness of your model, which is this will evaluate the consistency of clustering with different data splits or initializations. This is not only really like a unsupervised learning strategy. This could be also used for supervised learning, but something called cross validation. Um, I would familiarize myself with that if you guys aren't familiar already, but basically that helps your model be as optimal as possible. Um, and then the gap statistic, I don't know too much about that, but it evaluates the consistency of clustering. And then finally, visualization. We went over some visualizations today, but this will give you the most intuitive check of visualizing it in a lower dimensional space, as we did with the dimensionality reduction, and even above with the different clustering. Right. So those are some ways you should evaluate your unsupervised models. As you can see, the metrics, other than silhouette score and like this Davies Bouldin index, it's not like supervised learning models where we look at the accuracy, we look at the mean squared error of our regression after comparing it to our output labels. Um, Instead, we have like ways to interpret how well we made the clusters and maybe ways to go out and figure out what all of this means. And I would definitely look into these other external metrics, actually, ARI, NMI, V measure, cluster purity, because the external metrics seem like almost what's the most important part is because the whole goal of this is to interpret some things about your data set and then apply those interpretations. And so comparing the clusters to known labels if available seems the strongest thing to do. And so that wraps up the evaluation metrics and basically the whole workshop today. So I have a quick summary I'm gonna go over. I know I went way over, but we didn't really put time limits on these workshops for a reason. So, but anyways, summary. Clustering should always be viewed in context. Remember that to understand the data, pre-process it properly, and then evaluate the results using appropriate metrics, right? Should always be viewed in context. That's the most important part. Like all you could do all of this, but again, what does it mean, right? In this scenario, if these were two labels, I would assume that these were two different types of irises. Um, so yeah. Um, Another thing to do is experiment with different algorithms. Don't just be like, okay, k-means and dbScan is all I need, or like just k-means is all I need. I would definitely try multiple things out, especially with a lot of these lightweight models. It's not really costing you much to try them out. Try them out, sorry. And this is how you kind of see which model is the best one for the data's structure. And as you can see here, I said that try them out. They're good? They're common starting points, but the best algorithm depends on the data structure and on your specific goals. With this unsupervised learning. Um, and so now visualize and interpret is another important thing. Along with the domain knowledge, which is needed to actually interpret the clusters, there is no like ground truth to compare it against. So the best we can do is visualize our outputs. And finally, I want to say right now, and this is like the big thing, this is what I've told you today is not enough to be good at unsupervised learning, but it should be enough to get you started. These are like the basics of the basics, I would even say. So if you really want to go deep into it, please feel free to go out and do some outside research and actually apply it. Try it on some data sets on Kaggle. Um, just try it out. Try these things. See if you could visualize stuff neatly. Um, but yeah, this should just get you started. This should be enough to give you an idea of where to go in the upcoming Datathon. Um, even for the upcoming Datathon, if you want to do really good in our unsupervised pillar, I would look more into um external external metrics. And a big part of the unsupervised pillar is your ability to interpret what you're trying to do. Um, so yeah. And so that's the summary of our workshop today. I had a great time talking with you guys, and thank you for those in the Zoom who stuck around. I know it was a long one, but you guys are actually the best for keeping me company. Again, this is going to be posted um, tonight. I'm going to get it posted as fast as possible, and then I'll send that announcement out in the Discord. But yeah, so that's unsupervised machine learning. Um, so you guys are free to go. Thank you so much for sticking around. And if you have any questions, feel free to stay back and ask me them. I'll stay until everybody leaves. But yeah, you guys have a great rest of your nights and take care.